Hello everyone, I'm Yiran from Tsinghua University. Today I'm going to introduce you my research work, DOVE, Diagnosis-Driven SLO Violation Detection. As network develops, internet applications are having more and more strict service level objectives, or SLO for short, over reachability, packet loss, latency, and bandwidth. Today, SLO maintenance is gaining increasing importance. Let me show you a few examples here. Algorithmic stock trading and cloud gaming require constantly low latency to make full use of every financial opportunities in the market and have good playing experiences respectively. Along with latency requirement, industrial control system has more requirements on packet loss to never lose controls. Telesurgery and video conferencing have further throughput requirements to offer clear videos and audios. Block storage service and VR video streaming require high throughput and low packet loss to ensure high performance and good watching experiences. However, at the same time, SLO violation is common and destructive. SLO violations may degrade user experiences, cause monetary damage, pose security or function issues. For example, Google and Bing's report indicates that extra web visiting delay directly leads to revenue reduction. A survey shows the internet services from 9 Australian ISPs have severe latency jitters at busy time, which is unacceptable for many games. Amazon lost a lot of money due to a blackout accident. Another survey shows that in many data center networks, there are around 40 to 80 machines suffering from severe packet loss every year. Even at the moment, there are many IP prefixes having reachability problems. In order to reduce the damage brought by SLO violation, there are urgent needs to fast mitigate the network problems. Fast mitigation requires 3 steps. The first step is detection. Detection measures network performance at real time and compares the real performance with the expectation, that is to say, the objectives. When the network fails to meet the objectives, it should report to and notify the network operators. The second step is diagnosis. Diagnosis analyzes the causality of the SLO violations. In many cases, flow-level causal information is extremely helpful. The last step is troubleshooting. With flow-level causal information, network operators can do corresponding actions, for example, reset firewalls and reboot hardware to mitigate the problems. The detection and diagnosis are the key steps of all. Fine-grained and accurate detection gives network operators clear visibility into network performance. When bad things happen, detection makes operator know about them immediately. Diagnosis find out responsible culprit flows. When bad things happen, diagnosis makes operator know who to blame to solve the problem. Unfortunately, existing detection and diagnosis solutions have several drawbacks. Let's first take a look at detection tools. Traditional active and passive tools such as ping, netflow, SNMP work at coarse timescale, which is at second, even minute level. It cannot detect microbursts and provide fine-grained information. Packet mirroring techniques such as NetSet send packet information from the switches to the control plane. It collects exhaustive information and can verify SLO on the control plane. However, the traffic overhead of a NetSet is large and it faces scalability issues. End-host involved techniques such as switch pointer TPP need to modify network stacks of the end host, which is impractical in real network settings. Loss radar and INT-SITE can only test certain types of SLO, and they rely on control plane's computation capability to function, which introduces extra lags. Therefore, we need a new detection tool, which detects at fine-grained timescale, gets rid of control plane and end host to reduce lags, generates small traffic overhead, and monitors multiple SLOs. Existing diagnosis tools, for example, DEPR, DTAP, Provenance, can link events to its direct causes. In the network settings, in most cases, high queue occupancy is a direct cause of SLO violations. Exhaustive flow level queue information at arbitrary time is needed to let the tools work. NetSet can provide such information, but it generates too much overhead. Other detection tools cannot provide such fine-grained queue information. Therefore, we are facing a dilemma where there is no feasible diagnosis solutions to explain SLO violations. Therefore, we bring you Dove to first measure multiple service level objectives at fine-grained timescale with low lags and overhead. And second, collect causal information and diagnose the SLO violations. Let's look at some core concepts of Dove. Different from generalized processors such as CPU, the computation resources of the programmable data planes are extremely constrained. Detection requires high SLO verification accuracy without introducing the computation ability of the control plane. Hence, for detection, Dove only monitors partial set of flows, that is VIP flows, to measure their SLOs. Detection is completely based on the data plane, resources, and logics. We call the set of flows the selected flows. Diagnosis requires gathering more causal information to have more accurate violation explanations, which means watching more flows to find out potential bad ones. Hence, for diagnosis, Dove gathers causal information from a wider set of flows called the watched flows. The watched flows can use sketches to monitor a complete set of flows or use Sonata for periodic updates. The watched flows and the selected flows are not necessarily the same. They are empirical and set by network operators. Next, we look at epoch and segmentation. Dove splits continuous time into a series of adjacent epochs. The length of epoch is identical and configurable. Dove splits flow path into segments. The life cycle of a packet going through a programmable switch includes ingress MAC ports, ingress match action pipeline, queuing, egress match action pipeline, and egress MAC ports. A segment is from the ingress match action pipeline of the upstream switch to the ingress match action pipeline of the downstream switch. A physical switch can be a downstream and upstream switch at the same time for adjacent segments. Upstream and downstream switches do not have to be neighbor switches, which makes Dove support partial and incremental deployment. Note that for every selected flow, Dove measures its SLO on each segment during each epoch. Let's look at Dove's architecture and how it works. Dove consists of three components. On the data plane, SLO Violation Detector verifies the SLOs of the selected flows. It generates alerts and reports them to the control plane at the end of the current epoch if SLOs are violated. Suspicious flow behavior monitor checks the flow behaviors to find bad flows out of the watched flows. It generates events and reports them to the control plane if any suspicious flows are found. On the control plane, SLO Violation Analyzer passively collects all the alerts and events. It uses events to explain the causes of SLO violations. In the network view, the first Dove-enabled switch inserts telemetry headers into the packets of the selected flow. When these packets leave the network, the exit switch removes the headers. The analyzer also distributes epoch-wise and segment-wise SLO values within the configuration files to the switches. The SLO values are installed as thresholds. Switches collect and compute real network performance and compare it with the thresholds to decide whether to generate alerts or events. Let's look into SLO Violation Detector to see the mechanism to verify the SLOs. First, Dove measures packet loss using coloring algorithm, which completely runs on the data plane. Step number 1. Upstream switch dyes packets red or gray in turns. The packets of the same epoch are dyed the same color. This is done by setting the color bit in the telemetry header. Step 2. Switches red or green color increments when it sends or receives a packet in the corresponding color. Step 3. Upstream switch copies the counter value of the previous epoch into the telemetry header. Red packets carry the number of green packets, while green packets carry the number of red packets. Step 4. Upstream switch clears the control bit for the first half of the epoch and sets the bit for the second. At the beginning of the second half, upstream switch resets the counter of the previous epoch to prepare for the next epoch. Step 5. For the first half of the epoch, downstream switch stores the number of sent packets carried in the headers. When first seeing the set control bit, it calculates packet loss by subtracting the number of received packets from the stored number. Then it resets downstream counters of the previous epoch. Coloring algorithm is resilient to packets out of order and lost because it waits for half of the epoch to get the number of sent packets and then calculates packet loss. Next, DAF measures percentile delay using an approximation algorithm. It is difficult to measure flow level percentile delay on a data plane. However, instead of answering what is eta percentile delay, we only need to answer a yes or no question. Does eta percentile delay exist a certain threshold? Let's see how to answer this question. Statement 1, eta percentile delay is larger than d. Statement 2, let the number of value exceeding d be n. N is larger than n minus left floor n minus 1 times eta percent right floor minus 1. Statement 1 and 2 are equivalent if n minus 1 times eta percent is an integer. They are not equivalent if that number is not an integer. In this case, if statement 1 is true, statement 2 can be false, whose n is n minus left floor n minus 1 times eta percent right floor minus 1. However, considering it is rare that n happens to be exactly in that number, we can treat two statements equivalent. Here's the interesting part. We can then simply count the number of delays exceeding d and then compare the number with the threshold installed from the control plane. At last, SLO violation detector measures maximum delay of the current epoch. Next, we look into suspicious flow behavior monitor to see how it gathers causal information. Unlike SLO measuring, the monitor checks flow behaviors on each DAF switch instead of each segment during each epoch. Let's first ask what contributes to SLO violations. The causes are various. High queue occupancy, inter and intra-switch loop, etc. can lead to high delay. Queue overflow, link corruption and failure, software bugs can cause high packet loss. Among other causes, the most common one is queue-related cause, because the hardware, software, and configurations are relatively fixed compared with dynamic network conditions. Therefore, the monitor finds out the flows contributing much to the queue occupancy as the potential causes. The monitor finds first, heavy hitters, which are flows with large traffic, and second, heavy changers, which are newly established flows or whose traffic increases rapidly. Although the absolute flow rate may not be large, several heavy changers may break the balance and cause congestions at switches. The last component is SLO violation analyzer. Having collected alerts and events, the analyzer has to link certain events to the alert. There are two principles about the correlation. The first one is location adjacency. Heavy hitters and changers need to share the same queues with the selected flows whose SLOs are violated. The second one is epoch adjacency. The epochs of heavy hitters and changers should be close to those of the selected flows. Based on the principles, alerts can be correlated to, first, high queue occupancy at the upstream switch. The events are from alert's upstream switch sharing the same egress port with the alert, and the event's epochs are just before that of the alert. And the second is high queue occupancy at the previous switch of the downstream switch. The events are from the alert's downstream switch sharing the same ingress port with the alert, and the event's epochs are just before that of the alert. We implement DAV on P4 software switch, behavior model version 2, and barefoot Taveno, testify its effectiveness, accuracy, and overhead, and compare DAV with state-of-the-art works. We show DAV's effectiveness with the use case. We set up a simulation use Mininet with the topology shown in figure A. There are 4 switches, all of which are DAV enabled. Flow A is the only selected flow whose SLO should be maintained. The rates of flow A, B, C, D are shown in figure B. Figure C shows the accumulated flow rate with running time on segment S2 to S1. It also shows whether an alert is received on each epoch. We choose 2 alerts shown as diagnosis points on figure C to verify the effectiveness. The analysis results are shown in DAG. The first alert is mainly caused by flow B. The second alert is due to flow B, C, D. Note that this corresponds to the real traffic change. We evaluate Dove's bandwidth overhead. The bandwidth overhead consists of two parts, which are first, telemetry header, and second, alert and events. There is a trade-off between SLO measuring accuracy and overhead. A finer epoch length has deeper visibility into network status at the cost of generating more traffic overhead. The header overhead is proportional to the size of the selected flows. We evaluate Dove's packet loss and delay coverage rate. Compare Dove with state-of-the-art works. For packet loss, Dove achieves good coverage rate. It is worth noting that heavy packet loss makes coloring algorithm less effective, which reduces coverage rate. This is because all of the packets which belong to the second half of the epoch are lost. Without the set control bits, downstream switches are not triggered to calculate packet loss. Dove generates much less traffic overhead than NetSet and loss radar. As for delay measuring, Dove generates much less traffic overhead than NetSet and NetSet. We evaluate Dove's data plane resource utilization in several real network topologies shown in the table. For each pair of source and destination nodes, there are 512 selected flows and 512 watched flows. The TCAM usage of Dove is twice as much as that of NetSet. This is because Dove has two lookup tables for selected flows and watched flows, respectively. Dove's SRAM usage is more than NetSet, since packet loss measuring in Dove requires many registers used as triggers and counters. Dove's TCAM and SRAM requirements are within the resources of Tofino, which makes Dove deployable in real network settings. That's the end of Dove. Thanks for listening.